edge. Nothing is happening in this side. So first answer was that there is zero oxide grown. So region 1, X naught is 0 because silicon nitride has a mask for oxidation. So no O2 can diffuse through it. So there is no oxidation. So in this region, growth of oxide is 0. Second one was very straightforward. It is a bare silicon and we are doing steam oxidation. Okay, and then so you just go, you are given 1000 degrees, you know A and you know B, and you have to use tau equal to 0 here because some of you went and you took the tau for the dry oxide. But remember, for wet oxidation on the bare silicon, tau is 0. Only when you are doing dry oxidation, so some of you used a number 0.37, which is written somewhere in the table, but we forgot that this is steam oxidation. So you will just use an A and B, and that's it. Then it is very simple. You know, A and B and tau are known. So in region 2, you get a thickness of about 0.43 micron. So it is just oxidation of the bare silicon in the steam. That's all that question was. And you know A and B. Then up here, you have an oxide present. So when you do the oxidation, you have to find the tau based on this half a micron thick oxide. And most of you got that right. So first you get the tau corresponding to half a micron thickness, which is your d squared plus AD divided by B. Right? That's how you calculate the tau to take care of the initial thickness, and that gives you tau of 1.26 hours. And now you just use this equation, standard equation here, and this is d plus tau, and this gives you 0.7 micron. So this is what it is in A, B, and C. So there is 0 oxide grown here. Here there is 0.434 micron oxide grown here, and this oxide final thickness. This is not the oxide grown. Total thickness at the end, 0.5 will become 0.7. So the next question was how much silicon is consumed in this region. So how much extra oxide grew? 0.7 minus 0.5. So 0.46 of that is the silicon consumed here. So the answer to that question was that additional oxide grown in region 3 is 0.7, which is the final, and 0.5 is the initial. So 0.2 micron is all you grew in the region 3. So silicon consumed in region 3 is 0.46 times 0.2 is 0.092 micron. So then the point was that how come it only grew 0.2 micron here, and in this case it grew 0.4. So here you calculated 0.4 oxide, and here I only grew 0.2. It is for the same time and temperature. So the answer was that when you already have an oxide, the diffusivity decreases here because it takes longer time for the oxygen or H2O to get here, and this is what slows down the oxidation rate as the oxide becomes thicker. And then if you wanted to do mathematically, it is here that this is a thick oxide, so you are in parabolic regime. So if you do dx over dt, it becomes as a function of x, right? So if the oxide gets thicker and thicker, you know, the diffusivity becomes a problem, or availability, because it's taking longer for the thing to go through. So oxidation rate begins to slow down. So if you remember the graph we plotted, you know, oxide thickness versus the time, it goes like this, and in parabolic regime, it becomes slower and slower with time because oxide is getting thicker. So those were the two side questions here, that how much silicon was consumed in region 3 when you grew the oxide, and then the second was that this is slower because you have a thicker oxide. So that was question number 1B to A and B. Then the C was, a lot of you got all right, but some of you, I don't know. I went through this so many times, and I said questions like this would be on the test. So this was simple, that why you grow this trench, right? First question. So if you don't have a trench, and if you do this, I was just showing that if I grow this oxide, I will have a bump there, right? And now I have this topography is now up and down, and then you have this up and down thing, your photolithography will be bad because depth of focus becomes a problem. So I created unnecessary this undulation on the top without the trench. So what you do, you dig a trench, right? And you find out how thick an oxide I can grow. So when I'm done with the oxide and we remove nitride, I will have a flat region. So photolithography can be. So that was the reason that without the trench you will have the BEM or the bird's beak here, right? And then with this trench, you can think about how thick an oxide you need to grow. So the question was basically, if you now look at it, if I grow this oxide here, which I don't know at this time, I said this is T-ox, then it will eat up 0.46 oxide this. So total oxide thickness is what, 0.5 micron plus 0.46 x naught will be equal to x naught. So that's all it was. So if you realize what's happening in this trench, so x naught, which is the total oxide thickness, is the sum of 0.5 micron trench and 0.46 x naught that you ate, and that gives you x naught of basically 0.926 micron. Okay. So if you grow that 0.926 micron oxide total thickness, then you will have a flat area here with an oxide separating the device you will make here and the device you will make here. So that was the question. So it's not very difficult, but if you did not read the topic of low cost or local oxidation for isolation, right? So this is the local oxidation process used for isolating adjacent devices. So that was that, right? Then question 3 was about the diffusion. So you can see each chapter has a question. One was oxidation, one was diffusion, one is lithography, right? And then some general question in the beginning chapter. So this was just you do a pre-dep, okay, and it is giving you at 900 degrees for 15 minutes. And then I have 2 drivers. One is 1100 for 5 hours and 900 for 1 hour. That's your process in the lab, whatever. Then the first question is, tell me everything about pre-dep, right? So forget about the dry. When you go to pre-dep, I gave you the solubility here, right? Okay, so 1.2 10 to the 20. So in pre-dep, surface concentration is equal to solubility is equal to this. That's your answer. So this is one of the answer. The next is what is the dose, right? Dose is simply this equation here. So you calculate your dt. So I gave you the values of d here, right? And the time of oxidation is given. So dt for the pre-dep is 1 hour, right? So d is given to you, right? And time is 1 hour, 15 minutes is my pre-dep. So when you do this calculation, you just simply get this answer of 1.54 10 to the 14. So d is given to you, t is known, right? Time of pre-dep, and d comes from the temperature. So I already gave you the d values for temperature. And you put the time, CS is simply this, and most of you got this all right, the dose. This is the dose. Now then third is the profile. So there was surface concentration, dose, and profile. Profile is the complementary error function, and this is x divided by 2 square root of dt. So you know 2 square root of dt is this. This is the surface concentration. So these are the 3 very quick numbers, is all you needed to know if you've done the homework many times you gave. Next I asked that how would you change the pre-dep temperature and time to increase the surface concentration but keep the dose same? Okay, so we know that to increase the surface concentration means I need to have more solubility. So if I increase the temperature, I can take care of your requirement for higher CS. So first thing would be that you will increase the temperature, right? Because I'm asking for more surface concentration, which is equal to solubility. But then I want the dose same. So if you want the dose to be same, your DT product has to be similar, so you have to cut down the time. So you reduce the time and you increase the temperature. So that way dose is related to DT. So if I increase my D, I need to reduce the time, and that way my dose remains the same, right? Okay, next question is after driving. So this was about the PDAP. So I said, okay, give me all the information after you drive, and I've got 2 drive-ins. So you said, no big deal. All I have to do is to get my DT effective. That's all there is. So you said DT PDAP, DT first drive-in, DT second drive-in, and D and T's are given to you. So you just put those numbers here, and you find that this one dominates. So the first thing to do is to get the DT effective, which is 5.3 10 to the minus 9. So once I have DT effective, the whole game is over. You just use the CS is Q divided by square root of pi DT effective. So Q is known. Some of you, I don't know why it started getting a new Q. Q, I told you, never changes. It comes from whatever you had here, right? So Q is known, right? And DT effective is this. So you calculate the surface concentration after both the drive-ins. It comes out to be 1.2 10 to the 18th, right? Then XJ equation is simply here. So DT effective is known. Now you know the CS from the previous one. The base doping is given to you. That gives you the XJ of 2.8 microns, right? And the third thing is profile. This is all we need, is surface concentration, junction depth, and profile. And that is equal to CS, okay, and CS is this, exponential of minus x squared over 4dt. So this is what we needed to do that. So junction depth is 2.8 microns. So once you got this, I says, okay, tell me what is the sheet resistance. You got all these. There must be a sheet resistance, so that's the next problem. Okay, but I said to get the sheet resistance, use the Irwin curve, right? So I know the surface concentration and I know the substrate concentration, right? That's all I need to read the RSXJ. So you go into your, but it should be Gaussian because it has been driven. Error function is only that. So some of you started using this, but you go to, I did not draw the line. So you go to 1.18, okay, and then you read this and read whatever roughly that number is about 400 ohm micron. So you take the surface concentration, you take the base concentration, right, and then you come down and read the RSXJ. So once you have the RSXJ product, which is 400 based on what I read, okay, then XJ is 2.8 micron, so sheet resistance is 143. So it is just basically, not very difficult enough, based on